Today we're going to talk about geometric optics, which is the study of light as rays. A ray is a mathematical term for a straight line that originates from a point. Geometric optics is the part of optics that deals with rays and the ray aspect of light. Now, there are three methods for light to travel from a source to another location. First of all, light reaches the upper atmosphere of the Earth traveling through empty space directly from its source. Secondly, light can reach a person in one of two ways. First of all, it can travel through a media like air or glass. It can also reflect from some object like a mirror. In the situation shown here, light interacts with objects large enough that it travels in straight lines like rays. Now, the first law that you need to know and need to put in your head is what is called the law of reflection. The law of reflection states that the angle of reflection is equal to the angle of incidence, or theta subscript r is equal to theta subscript I. These angles are measured relative to a perpendicular to the surface, which is called the normal, at a point where the ray strikes the surface. Now, in most situations, light is diffused because it strikes a rough surface. Here, parallel rays strike a rough surface, but they are reflected in many different angles since the surface is rough. You can see that various normals are drawn at various points in this rough surface, and this results in each one having its own angle of reflection and causing a diffusion of the light. When light hits a sheet of paper, it is illuminated by many parallel incident rays. However, it is seen at many angles because the surface of the paper is rough and diffuses the light. A mirror, on the other hand, when illuminated by many parallel rays, only reflects them in one direction since its surface is smooth. Only the observer at a particular angle will be able to see the reflected light. Now, here's a problem that comes from this previous discussion. Here we have an image on a mirror, and the image is behind the mirror. The two rays shown are those that strike the mirror at just the correct angles to be reflected into the eyes of the person. The image appears to be in the direction the rays are coming from when they enter the eyes. Now, this problem is as follows. Suppose this girl is 5 feet tall and she has a hairdo that extends 1 foot above the top of her head. Her eyes are exactly 5 inches below the top of her head. To see her entire image, including the top of her hair, there are two questions. What is the minimum length of the mirror? And how high must it be hung? Now, in order to do this problem, we have to take a look at this like a geometric problem. So let's draw more simply, as it turns out, this previous diagram right here. So we have the top of her hair, the top of her head, her eyes, and then the bottom of her feet. And what you can see here, let me get rid of that extraneous little marker. What you can see here is that, first of all, this is the top of her head. You'd have to, at the top of the mirror, which is right here, you have to have a angle of incident and angle of reflection that are equal. Secondly, these are her eyes again. At the bottom of the mirror, you have this. Now the mirror is actually going to be straight. I'm just not very good at drawing. So let's take, for example, this. Let me try that again. Here's the top of the mirror and the bottom of the mirror. Okay, so the distance from the eyes, this is 5 plus 12 or 17 inches. And this is 60 inches, 5 feet minus 5, so this is 55 inches. And half of 17 inches is 8.5 inches. So it's going to be 8.5 inches above and 8.5 inches below. And this point is going to be exactly 8.5 inches above the eyes. And half of this is 27.5 inches. So the distance from the eyes here down to the here has to be 27.5 inches. So this is 27.5 and this is 8.5. So the total length of the mirror has to be the sum of those, or 36 inches. Now, how high does it have to be hung? Well, it has to be hung exactly 27.5 inches above the floor in order for the feet to hit at the very bottom and reflect up to the head. Now, in addition to reflection, there's a phenomenon known as refraction. And when you look at a fish tank, you can see that the fish are shown in different locations, and they seem to change direction when the light from the fish passes from the air to the water, or from the water to the air, excuse me. In this case, the light can reach the observer by two different paths, and so the fish seem to be in two different places. This bending of the light, as more accurately shown right here, is called refraction and is responsible for many optical phenomena that we observe. Now, in order to understand refraction, we have to understand something about the speed of light. And this is what's known as the Michelson apparatus. The Michelson apparatus was used to measure the speed of light. And what you see here is a source that fires light into a rotating mirror. And what you do is as this mirror rotates, it reflects to the stationary mirror, but these two have to line up exactly the right way in order for the observer to actually see the light. So you can look at the speed with which this rotates and these distances and calculate the speed of light from doing this. And they were able to calculate the speed of light within 0.04% of the actual value that's now known. So the speed of light is 2.9972458 times 10 to the 8th meters per second. I just usually tell students to use 3.00 in virtually all of their calculations. Now this speed of light that's being used here is in a vacuum. The index of refraction is the speed of light of any material. The index of refraction of any material is the speed of light in a vacuum, which is this number, divided by the speed of light in the medium, air, water, glass, etc. So the index of refraction is going to always be some number greater than 1 because the speed of light in a vacuum is as fast as it can possibly go. Now, refractions cause the light rays to bend, as we said, and this light ray bending depends on whether the incident ray enters from the side in which it travels faster to slower, in which case it bends toward the normal. So from faster to slower, if the light ray slows down, it bends toward the normal. Conversely, if it goes from slower to faster, it bends away from the normal. Away from the normal, or slower being the grass in this example, and the sidewalk being faster. So when it moves closer to the perpendicular, if it slows down. and it moves away from the perpendicular if it speeds up. And the law of refraction states that the speed, the index of refraction in one medium times the sine of this incident angle is equal to the index of refraction in the second medium times the sine of the refracted ray angle. Similarly, in this case, it would be this index times the sine of this is equal to this index times the sine of this. Now, in a situation where you go from a slower to a faster situation, you see that the incident ray has angle theta 1 and it bends away from the normal because it's going into a faster medium. So angle theta 2 is greater than angle theta 1. So it bends away from the perpendicular. So you can see there's a point you're going to reach where it does not escape. It's 90 degrees. And that is called the critical angle, or theta c. It's the angle in which the refracted ray angle is 90 degrees, or the sine of 90 degrees is 1. And here we have anything larger than this critical angle results in what is called total internal reflection. So the sine of the critical angle is equal to 1 over the index of the slower medium, Now let's do this problem. Light passes from red flint glass, which is given an angle or index of 1.585, into water, which has an index of 1.33, at an angle of incident of 28.1. What is the angle of refraction? So this is pretty straightforward. So first of all, we know that medium 1 times the sine of angle 1 is equal to medium 2 times the index of refraction, medium 2, times the sine of angle 2. So that means that the sine of angle 2 is equal to the index of 1 times the sine of angle 1, or incident if you want to use that word, divided by the index of refraction 2, and that angle 2 is the arc sine of this quotient here. And so let's put the numbers in here. It's going to be the arc sine. Now 1 was 1.585 sine 28.1 degrees divided by 1.333. Now, or 1.33. Now you would predict, because it's going from a more dense to a less dense material, and that means that the angle will be larger. So you should get a number that's larger. So if you do the math here, you actually end up indeed with the angle 34.1 degrees. Now the second part of this problem states that the ray is going in the reverse direction, and the angle of incident is at 16.8. Now it's going in the reverse direction, so the angle should get smaller instead of bigger. But the formula is exactly the same. So let's just write it down. It's going to be arc sine of n. Now it's going to be n2 sine theta 2 now, because we're going in the opposite direction, over n1. And now this is going to be 1.33 sine 16.8 divided by 1.585. And indeed, when you do this math, theta 1 is going to equal 14 degrees.